Yeah. It's so great to be back in person. So much so that I forgot how a mic works. Thanks, Bill, for inviting me. So I'm going to be talking about MLOps, and of course, I'm going to be talking about it a bit controversially. I'm going to say, you don't actually need MLOps. To kind of set the stage, right? So I just want to know, where everyone is. Hands up if you do machine learning at work. If you have a machine learning, okay, so keep your hands up if your machine learning model is in production. So people are actually using it to make decisions, customers are doing it, okay? Keep your hands up if you have multiple machine learning models at work. Okay, and keep your hands up if those models share features that you pre-compute. Okay, and keep all right. One person
Clarifying question.
I'm sorry.
A clarifying question.
Yes.
How many of the models have to share how many of the features?
As long as you have one feature, one embedding that is pre-created, and you share it among multiple models, you can keep your hands up. Okay, and how many of you have models that are automatically detecting drift and being retrained if it's drifting? Okay, so we have 1, 2, 3 people in this room who need MLOps. Okay, so and now we have 30 minutes left. Okay, so let me go ahead and talk about why, lots of times, right, you basically get these buzzwords in industry and we think that, oh my God, unless I do all of those things, I'm not actually doing it the right way. And what I'm trying to be here to say is that, no, you don't need all that complexity. Keeping it simple and getting things into production is the most important thing. And in many ways, those of you who started to put your hands down are doing it the right way because you're recognizing that you don't need all that complexity. Okay? So you hear a lot about MLOps, right? So what exactly is MLOps? Well, it started it's basically like the whole DevOps thing, right? DevOps is DevOps, or MLOps is DevOps for ML systems. Right? And when you think about why did DevOps come about? It came about because it used to be that software developers would develop models and go give them off to production. They would kick it off to a production team, a QA team that was basically in charge of essentially maintaining those models and fixing them, except when a problem came along, those teams didn't know anything about the software itself and they couldn't fix it. Right? So the whole idea behind DevOps is, let's have the people who are managing and monitoring software systems be able to fix them also, right? So the whole idea was for operations people to be able to administer software. And this kind of started off with the large tech firms where they started to hire SRE roles, site reliability engineering roles, where you had essentially programmers who were capable of making small changes to software systems so that you didn't have this big wall where you had to basically cross software over. MLOps is exactly the same thing. The whole purpose of MLOps is so that the operations people, the people who wear pagers and who get called, can make small fixes to machine learning models. So that the data scientists who are developing models do not have to be on this whole 24/7 call routine. Right? So when you step back and say, what's MLOps for? It's just for that operationalization. Okay? So this all started with this very viral image. You cannot have a talk on MLOps without having that image from the Scully paper, right? And the basic thing is called Hidden Debt in Machine Learning Systems, an awesome paper. It started the whole MLOps trend, and the key thing there was that the ML code that you're writing, your XGBoost code, is a really, really, really small part of the overall ML system. right? There's a lot of other work that has to go on before you can take your machine learning code and put it into production, right? So the idea is that you can develop your ML system super cheap, but the reason that you need everything else, you need to basically make sure that you're collecting data in a good way, make sure that you're serving it, make sure that you have loosely coupled systems, is because maintaining those models over time is very, very, very expensive. It's very difficult, and you have to realize that with machine learning, you're not just maintaining code, you're also maintaining data. And data also changes. The environment in which the machine learning models work also changes. And that was what the Scully paper was talking about, and was saying, whenever you deploy machine learning models, remember that you have to basically, you're putting it in an environment that changes over time. And therefore, your operations people have to be able to make changes, right, to your machine learning models, to understand changes to the data that cause the ML models to no longer work correctly, and those need to be fixed. Absolutely true. And when the Scully paper came out, I was still a practicing data scientist. So this was like 2015, and the 2010s, this was like exactly the problems that I was facing. Like that, everyone who was developing machine learning models in the 2010s was facing the problems that the Scully paper was talking about. So one of the problems that I was working on is that this is a weather radar image. Okay, so weather radar image, it's basically anything in the atmosphere that reflects weather radar beams is going to basically show up in the image. So out here are thunderstorms, but these here are bats. Okay, so obviously, if you're going to basically feed a weather radar image into into a numerical weather model, you need to remove the echoes that correspond to bats, right? So so one of the things that I was working on was a neural network that would basically take an image that looks like this and basically create an image that looks like this. Remove the stuff that is not meteorological, right? So in order to do that, we have to basically take the radar data, which basically a radar sits on the ground and sweeps it, right? So it's a cylindrical thing. We need to take the data, we need to remap it, we need to create images out of it. We need to basically, some of these things are easier to handle than others. And this was again 2010, we did not have the kind of GPU computation that we have today. So basically classify the easy pixels with one ML model that was much simpler, and then take those things and basically like the radar scans up and down. So combine them in 3D volumes, compute a bunch of features, and then train another neural network to classify quote unquote the harder pixels, but these pixels always have errors. So you basically do post-processing of those things with segmentation models, and then having done all this on the training, we need to basically make sure that we are doing exactly the same thing when we are going and doing the prediction. All of the pre-processing that we needed to do had to be done exactly the same way, and we didn't have TensorFlow, we had this thing called Stuttgart Neural Network, SNNS, and that was basically, in order to, I had to take that neural network, recode it in C++ because our production system was in C++. So this is basically what Scully was talking about, and all of this stuff we had to essentially do, right? Those of you who had your hands up, you said you have your ML models in production. How many of you still recode your neural network so that you can put it into production? You don't need to do that anymore, right? If you're using PyTorch, you're using TensorFlow, you're using, even if you're using MXNet, right? It all still works, right? The same code works whether you're training or you're basically doing prediction. The point is that the problems that Scully was talking about have in many cases been fixed in the frameworks that we are now currently using. And if you're using TensorFlow, you're using PyTorch, you're using Keras, a lot of it has become a lot simpler. Okay, so what the whole idea behind MLOps is that you want to basically be able to build, deploy, and operationalize machine learning models very quickly, very rapidly, right? And that aspiration is absolutely real because that's a problem that we're going to be trying to solve. So all of this seems pretty good, right? Of course, we want to be able to deploy models. Of course, we want to do it in a lot simpler way. But the problem is that when you delve next level to it, the basic idea is that you have your data, you have to validate it, prepare it, train the model, evaluate the model, validate it, and then you need to basically go put it into deployment. And then whenever you're doing a prediction, you need to basically repeat these steps. And in order to do that, the basic suggestion is go ahead and basically formalize each of these steps and automate them. The formalizing is perfectly fine. The automation is a problem. But the whole reason for all of this is so that, again, I just want you to keep in mind, the purpose of MLOps is so that ops people who are not machine learning scientists can still administer ML models, can monitor ML models. That way we take all of our code and we give it to them and they can run it without having to understand all of the reasons why your objective function is the way it is. Right? They just need to be able to retrain the whole thing without needing to understand all of the code that went into that model. But now there's a problem with automation, right? And this is a problem that, like, there's a great comic from XKCD that basically is like, hey, here's this thing I'm doing over and over again. I don't want to do it over and over again, so let me go ahead and automate it. And your idea is, here's the work on my original task, and because I'll do a little bit of work to automate it, my job will basically go down to zero because the automation is going to take over. Well, that's in theory. In reality, though, right, what happens is you start to write the code, you start to debug it, this automation, and you basically start to develop that automation stuff, and the work that you're doing for automation is sometimes a lot more than the original work in the first place. Right? This is a common problem, right? Automation basically takes a life of its own, and you end up basically developing for developing's sake, even though this original thing that you could have done manually once in a while was perfectly fine. It's perfectly fine. So with that lens, let's take a look at what a typical ML ops system looks like. This is on AWS, okay? There's a spaghetti code of Lambda functions everywhere. API gateways, having to have a cloud transformation Terraform script, having to have a pipeline system to basically track your experiments, having to basically put the model monitoring in SageMaker, and basically being able to look at the SageMaker stuff and take the SageMaker logs and parse them and do stuff to them. If you're going to be building the system, how much time are you going to be spending developing ML models? Right? And that's a problem. That's the problem. Automation takes over, and you're now basically doing software engineering. You're no longer doing data science. Okay? This is not just, I don't want to pick on Amazon. This is Google Cloud. Same problem, right? You basically want to go ahead, here you're a data scientist, you want to basically get the data from your data warehouse, you want to train your model, and you want to deploy the model. But what does the automation mean? You now have to have containers for data extraction, containers for validation, containers for preparation. You have to create Docker containers for each of these steps, supposedly, right? You need to create a Docker container for training, one for evaluation, one for validation. Put all of these things in an ML pipeline, deploy it to Vertex AI pipelines, make sure you register the model in the model registry. Come on. Databricks, no different. Databricks, in fact, even worse. All of these is not even Python code anymore. These are all notebooks, right? Notebooks, which you and I know, our notebooks are like the worst form of code possible. Right? We just cannot keep track of any of the state management that we do. We're creating a whole bunch of diagrams that were supposed to be one-off, and now we're automating all those diagrams, right? Automating the running of these notebooks. So now you're supposed to have a separate notebook for feature engineering and training and evaluation and redeploying. Who does this? Right? You basically have cells. that do all of this. You have one monolithic thing, and you say, okay, I'm going to go basically automate this thing. That's essentially the problem, right? And the problem, so you're spending so much time doing the automation, you're not solving the business problem anymore. Azure, same thing. I won't go into this, right? Regardless of which of these things, once you say I'm going to do MLOps, and MLOps is about automation, you have a problem. You have a problem because automation is going to take over everything that you're going to be doing. Okay? So the thing is to step back a little bit. Like, remember the original intent. The original intent is you want to make your software for data science in such a way that other people, other than you, can administer those ML models, but you don't need full automation for that. Right? For number one, many things that used to be hard are now very automatic. Okay? So I was talking to you about my whole image classification pipeline. It's an image classification, it's an image segmentation model, right? I was talking to you about that. A whole bunch of stuff was in feature engineering. Do we still need feature engineering for image classification or image segmentation problems? No, right? The whole point of the deep learning models, the whole point of all of those layers and transfer learning is that you basically can pick out those features in an automated way. It's built into the model itself. So you don't need feature engineering if you're solving image models. It used to be that if you're doing text models, you needed to do stop words, you needed to you needed to basically remove punctuation, you needed to remove your stop words, you needed to do a whole bunch of stuff around bags of words and frequencies and compute like TF-IDF and so on. Do you still need to do all those things? No, right? You have a sentence, you throw it into BERT and out gets the embedding, and you train a model with that embedding. So much simpler these days, right? You don't need to automate something that today, over the last 10 years of machine learning evolution, has become a lot simpler and that is now automatic. But everybody who's building MLOps systems still thinks that your text processing pipeline requires all that complex stuff. It doesn't need all that complexity anymore. Right? It's a lot simpler. Secondly, a manual step is okay if it is rare enough. Drift detection. You're going to spend a year and a half building an automated drift detection system when it is something that people can eyeball and tell you this graph is going down. Right? So just have somebody look at the graph once a week. It's going to be a lot simpler than building an automatic drift detection system. Okay. Third thing, you can teach ops people new tricks. Okay? They're perfectly capable of going and looking at GPU utilization. They're perfectly capable of looking at RMSE scores. They're perfectly capable of looking at the difference in distribution between the original training data set and the new production training. Like, they're perfectly capable of eyeballing a few extra graphs. That's what they do for a living. They look at graphs of monitoring systems and they figure out when things change, and they can totally do that if you show them the graphs they need to look at on your ML systems. You don't need to automate all of that. So, let's again, like first principles. What are some of the reasons why Scully was talking about technology that's building up? The first and most important thing is what's called training serving skew. This is where when you trained your ML model, you did a bunch of pre-processing steps, and you forget some of those steps when you basically do it in production. And now the training system is different from the prediction system, and so these two pieces of software, the training stack and the serving stack, they're different. And when they're different, things don't work correctly anymore. Okay? Secondly, right, you might have clients who basically need multiple steps, and each of those steps is but of all of those steps, only one of them is an ML model. All the others are things like rules, etc. The problem is that you want to basically make sure that all of those rules are being applied in exactly the same way, because that's what you tested, right? Third thing, incoming data changes characteristics, right? So you trained on some piece of data, and over time the production system is now different, and so the incoming data is different. Or the correct answer changes over time. This is very common in recommendation systems, right? You basically now have a new product and you want to basically start to essentially recommend this new product, right? So the correct answer is now different. Or you have model fairness issues. You trained on a system where you had no college students in your population, and then you deploy in a system where there's a bunch of college students, right? Now those college students are not being treated in a correct way. Model fairness issues arise. Or parts of the system, right, aren't changed because you basically had a bunch of library dependencies. One of those libraries, you basically change the version of it, something is subtly different, and things don't work anymore, okay? Or, like, this is very common in like regulated industries. 3 years from now, somebody sues you and says, right, the loan like that you rejected for me was wrong. You should not have rejected me, and you need to go back and resurrect the system as it was 3 years ago, so you can basically show why you made the decision that you did. Right? So you need to be able to basically troubleshoot old results. These are the reasons why you basically have this technical debt in ML models. These are things that cause problems that monitoring people need to find out and fix. And the whole idea with MLOps is, how do we make this easy? The automation solution to these, I think we all hear about this. One way to avoid training serving skew, have a feature store where you compute the features that you need to be using, and it's in a feature store, and just look them up. And because you're just looking it up, I mean, how hard can it be? You're not going to basically get a skew between training and serving. Absolutely true, right? So you can use a feature store to limit the amount of training serving skew. You can use ML pipelines to basically make sure that the steps are being carried out in exactly the same order. You can basically do continuous evaluation to catch the incoming data changing characteristics. Whenever things change over time, make sure you retrain your ML model, so you set up a continuous training system. Model fairness issues, it's supposed to work. I've never seen somebody explain how it's going to work. Okay, so some reason why automation is going to automatically find why it doesn't work. Okay, new code gets checked in, you want to do it, use CI/CD, that will fix the problem. You want to be able to troubleshoot old results, make sure that you check in all your models and you basically have a history of them. If you have a history of them, you can basically go get the model as of 2 years ago and rerun it, problem solved. So the automation solutions totally work, right? And this is the reason why these are getting developed. But my point is, there is also a keep it simple solution for many of these things. And you don't need to go full automation unless you need to, right? So for example, right, there's a whole class of ML problems for which feature engineering is now unnecessary. If I were to do it today, I would not need to do, right, I would need to get my radar data, but the radar data today is streamed in by the National Weather Service directly into S3 and into GCS, right? Those guys have taken care of this whole data collection issue. It's already there in the public cloud. All I need to do is to basically train and deploy from it. So all of the stuff that I needed, not necessary. I don't need to do any of the easy classification, hard classification, feature engineering, because I can just use a UNet model. Each of its layers are going to basically learn what kind of features it needs to pull out. And I don't need to worry about rewriting your ML models, because I can just export my TensorFlow model and I can deploy it to Vertex AI and I'm done, right? If I need to do this in streaming, great. My Apache Beam pipeline will basically invoke the ML model. My data infrastructure, my ML infrastructure, my ML platforms have greatly evolved so that this is not a problem anymore, okay? So what do you need to do? You basically have to essentially take all of the transformations that you're doing and move them into the ML model itself. In Keras, it means that all your pre-processing is a Lambda layer. Do that when you export the ML model, all of the transformations get exported along with it, automatically get applied, problem solved. You don't really need a feature store. Not unless you basically want to pre-compute these features. Right? If it's code, you can basically put the code in your ML model and be done. Right? So the simple solution here is the transform pattern, which is to basically take the transformation code and throw it directly into the model when you export it. Same thing, right? This problem, this whole idea that you want to be able to call an ML model with multiple steps, not a problem. You can basically go deploy the ML model as a web API, right? So you basically set up a stateless serving function and the problem gets solved. Okay. Continuous evaluation is usually overkill. You don't really need continuous evaluation. All you need to do is to have a scheduled query. Every one of your data warehouses that you're using today, whether it's BigQuery, whether it's Redshift, whether it's Snowflake, they all let you do a scheduled query. Just schedule a query that does the evaluation and basically get the results out. It's a report, right? It's easy to schedule reports. You really don't need continuous evaluation. All you need is scheduled evaluation. Because face it, right? Even if you get continuous evaluation, it's not like you're going to look at those results every second of every day, unless you fully automate stuff. Unless you're able to look at the evaluation results and automatically do something. If that's not the case, doing the scheduled evaluation once a day is probably enough, and or having it be part of the thing that the ops person does is reasonably enough. If the correct answer changes over time, you can basically set up a systematic trigger. In a recommendation system, when does a correct answer change? Whenever you have a new product catalog land, right? If that happens once a week, just basically retrain once a week. It's a systematic trigger for when you have this new product catalog. Model fairness issues arise, you need to do sliced evaluations. Those can be done manually, right? Whenever new code is checked in, you want to make sure that you're rebuilding everything. Sure, just make sure that you're rebuilding from scratch, right? You don't have to basically go figure out that one component that changed and rebuild only that one component. It makes sense if you have a mono repo like Google, right? Which is like the entire company's repo. But that's not a problem that many of us have. And if that's not the case, a from scratch build is perfectly reasonable. You could do that, right? You want to troubleshoot old results, make sure you version control all your deployed artifacts. Your deployed artifact is a file, for heaven's sake. A model is a file.